Hello and welcome to my YouTube channel called Training Made Clear. Today's lesson is Industrial Communication Protocols, Part 2 of 8. Before we continue with the lesson, just to help you find all my other training videos, type in Training Made Clear into the YouTube search bar. For my fun channel, type in Percy's Discoveries. Industrial Communication Protocols. This series of 8 courses will cover the following courses. Course 1, TCP/IP Communications, Industrial Ethernet, and Yokogawa Brain Protocol. This course is Course 2, Introduction to Industrial Communication Protocols. Course 3 is HART Protocol. Course 4, Foundation Fieldbus. Course 5, PROFIBUS. Course 6, Testing and Troubleshooting. Course 7, Yokogawa Brain Protocol. Course 8, Modbus Gateway and NFN. This module covers Part 2 of 8 parts. Course 2, Introduction to Industrial Communication Protocols. Chapter 1. What is industrial communication? Imagine a factory with hundreds of transmitters measuring pressure, temperature, flow, level, valve position, motor speed. There you can see a two-wire transmitter configuration and a display of the instrument. So years ago, every transmitter sent only one electrical signal, usually 4 to 20 milliamp, back to the control room. The operator could only see the measured value. Example, the transmitter, pressure transmitter out there in the field, the output from there is 12 milliamps. In the control room, the pressure equals 500 psi. Nothing else could be seen. Modern instruments are much smarter. Today's instruments can tell the control system their tag number, their serial number, manufacturer, calibration date, sensor temperature, alarm status, faults, configuration, software version. All this information is sent using a communication protocol. A simple example. Think of two people talking. Person A speaks English. Person B speaks French. Neither understand the other. Communication fails. Now, imagine they both speak English. Communication works perfectly. Industrial instruments work the same way. Every device must speak the same electronic language. That language is called a protocol. Chapter 2. What is a communication protocol? A communication protocol is simply a set of rules that allows two electronic devices to exchange information correctly, exactly like the rules of a conversation. For communication to work, both devices must agree on how data starts, how data ends, the speed of the communication, error checking, address of the device, and the type of information being sent. Everyday examples. Your cell phone uses communication protocols. Examples include Wi-Fi, Bluetooth, USB, Ethernet. Industrial instruments use HART, Foundation Fieldbus, PROFIBUS, Modbus, Brain, Ethernet IP. Different industries choose different protocols. As you can see, there are many protocols. Why are protocols needed? Without protocols, instruments cannot communicate. Information becomes corrupted. Devices cannot be configured. Fault finding becomes difficult. Automation becomes impossible. Protocols allow reliable communication, faster maintenance, remote configuration, diagnostics, reduced wiring, lower maintenance costs. Chapter 3. Analog communication. Older transmitters use 4 to 20 milliamps. Only one value is transmitted. Example: tank level equals 60%. Current equals 13.6 milliamps. Nothing else is available. No diagnostics, no alarms, no configuration. Only one number. Digital communication. Digital communication sends many pieces of information. Example: pressure, temperature, sensor status, calibration, tag number, manufacturer, fault codes, configuration, all over the same communication cable. Let's do a comparison. Analog versus digital. Analog has one value, digital hundreds of values. Analog 4 to 20 milliamps. Digital messages. Analog is simple, digital is intelligent. Analog is limited information, digital complete diagnostics. Analog cannot self-diagnose, digital has self-diagnostics. Chapter 4. We'll be doing common industrial protocols in this chapter. The first one is HART. It uses 4 to 20 milliamps plus digital communication. It's very popular, easy to install, and can replace older transmitters. HART is Highway Addressable Remote Transducer. It's a hybrid analog digital industrial automation protocol. It superimposes digital communication signals onto legacy 4 to 20 milliamp current loops. This allows smart field instruments to transmit primary analog process data while simultaneously sharing diagnostic configuration and multivariable digital data over a single pair of wires. Foundation Fieldbus. Pure digital communication. No analog signal. Many devices share one cable. Excellent diagnostics. Definition of Fieldbus. Field and bus make Fieldbus. A field is a geographically limited area. In an engineering world, it is intellection of the plant levels. Bus, on the other hand, is a set of standard line that electrically links multiple circuits for transferring information. The idea behind Fieldbus is to eliminate any point-to-point links between the field devices like actuators and sensors and their controllers by a single digital connection on which all information is communicated consecutively in serial order and multiplexed over time. In most cases, the Fieldbus transfers the information in small packets in a sequential manner. The subsequent transmission of information decreases the total required number of connecting lines over greater distances than that of parallel transfers. PROFIBUS. Used mainly in Europe. Fast communication. Common on PLC systems and large factories. PROFIBUS, Process Field Bus. In a standard digital communication protocol used in industrial automation to connect controllers like PLCs to field devices such as sensors, actuators, and drives. It replaces complex multi-wire setups with a single network cable, streamlining data exchange. How it works: master-slave architecture. Master devices, controllers, control the data flow by polling slave devices, which are sensors and actuators, in a repeating deterministic cycle. Token passing manages writes between multiple masters on the network, so only one device transmits data at a time. Standardization openly published under IEC 61158 to ensure reliable multi-vendor device compatibility. Modbus. It's a simple protocol, very common. It has low cost and used on PLCs. Modbus instrumentation installations typically feature field sensors or drives wired via an RS485 daisy chain network to a central PLC RTU or Modbus Gateway. Communication model. Modbus uses a master-slave model for communication, client-server in Modbus TCP. Data representation. Classic Modbus has two transmission modes, ASCII and RTU. Modbus transactions. Modbus transactions use hexadecimal character instructions. Conclusion. Modbus allows PLCs to communicate with all kinds of remote units, including I/O banks, terminal units, and other controllers by relying on a standard method to read and write both discrete and integer information, covering nearly every scenario that involves the transfer of digital data. Modbus Gateway and NFN. The Modbus Gateway provides a communication link between networks that use the Modbus TCP communication protocol and fire alarm control panels FACPs resident on the NFN network. Modbus TCP. Modbus TCP is a communication protocol designed to allow industrial equipment such as programmable logic controllers, computers, operator panels, motor sensors, and other types of physical input-output devices to communicate over a network. Modbus TCP/IP uses TCP/IP and Ethernet to carry the Modbus messages structure. NFN Notifier Net. The Notifier Net Intelligent Fire Alarm Network links multiple Notifier Intelligent Fire Alarm control panels together as one. Each fire alarm panel on the Notifier Net maintains individual programming and continues to operate independently yet cohesively as part of a unified network. Here's the connection method for the brain protocol, developed by Yokogawa, similar to HART, mainly used on Yokogawa transmitters. The Yokogawa brain protocol is a proprietary digital communication protocol developed by Yokogawa Electric Corporation for industrial process automation. It allows smart field instruments such as pressure, temperature, and flow meters to simultaneously transmit digital setup data over standard 4020 milliamp analog signal wires without interrupting the core process loop. Brain BT200 brain terminal. As a portable terminal, the model BT200 brain terminal is used in combination with equipment used in brain communication for setting, changing, displaying, and printing out parameters such as tag number, output mode, and range. Through simultaneous communication, it also monitors I/O values and self-check results, sets constant current output, and allows zero adjustments. HART protocol, Highway Addressable Remote Transducer. What is HART communication? In addition to the 4 to 20 milliamp signal on the two wires in transmitters with HART protocol, a HART FSK frequency shift keying signal is superimposed on the analog value. How this works. The HART signal is made up of two frequencies, 1200 Hz and 2200 Hz, representing bits 1 and 0 respectively. Since waves of these frequencies are superimposed on the 4 to 20 milliamp signal as shown, the ancient way to send messages was using smoke signals. This is a digital over analog signal. Looking at the ones and zeros on the middle diagram, we see 100110110. This looks like a binary number, and we can calculate its decimal value. See the next slide. From the previous slide, we saw that HART signal is made up of two frequencies, 1200 Hz and 2200 Hz, representing bits 1 and 0 respectively. Since waves of these frequencies are superimposed on the 4 to 20 milliamp signal as shown. It sounds very similar to the Morse code method of communication. More modern way to send messages was Morse code signals like SOS, which means save our souls, an emergency cry for help, represented by 3 dots, 3 dashes, and 3 dots. Dots would maybe be 1 second flash of light, and the dash would be 3 seconds long. From the previous slide, the number 100110110 looks like a binary number. To calculate the decimal value, it is done as follows. We look only at the numbers with 1. So 100110110. We've made all the ones green. So the first number is 2 to the power 0, which is 1. Then 2 to the power 1, which is 2. 2 to the power 2, which is 4. 2 to the power 4, which is 6. 2 to the power 5, which is 32. And 2 to the power 8, which is 256. If you add all these green values, it'll equal 310. So this is the decimal value for a binary of 100110110. To check the decimal value, the decimal number 310 for binary value, you do it as follows. 310 divided by 2 equals 155, remainder 0. 155 divided by 2 equals 77, remainder 1. 77 divided by 2 equals 38, remainder 1. 38 divided by 2 equals 19, remainder 0. 19 divided by 2 equals 9, remainder 1. 9 divided by 2 equals 4, remainder 1. 4 divided by 2 equals 2, remainder 0. 2 divided by 2 equals 1, remainder 0. 1 divided by 2 equals 0, remainder 1. Write down all the remainder numbers starting at the bottom to the top, and you will have the binary equivalent for decimal 310. Binary equals 1, 00110110. Remember, digital communication sends many pieces of information. Example: pressure, temperature, sensors, status, calibration, tag number, manufacturer, fault codes, and configuration. Part of configuration can be the date of calibration. Let's say that the date is 22/7/2026. Now consider if this decimal date was converted to binary. This is what the digital signal will be when you configure the date. 22 equals 10110, which is 16 plus 4 plus 2 plus equals 22. 7 is 111, which is 4 plus 2 plus 1 equals 7. 2026 is 1, 2, 3, 4, 5, 6 ones then 0, then 1, then 0, 1, 0, which is 1024 plus 512 plus 256 plus 128 plus 64 plus 32 plus 8 plus 2, which will give you 2026. HART signal is made up of two frequencies, 1200 Hz, which is a 1, and 2200 Hz, which is a 0. So the date would be a signal which would look as follows: 10110 111, and 5101 010. All the 1 bits will be the 1200 Hz frequency. All the 0 bits will be the 2200 Hz frequency. If you hooked up an oscilloscope on the transmitter terminals, when this command is sent from the configurator to the transmitter to the input date, you would briefly see this signal shown like the picture above. This picture below will help you to visualize how the digital signals are sent across the analog signal wires to represent configured values asked for or new values configured during calibration. See how much more information can be sent using HART protocol. Before this, only the process variable could be seen based on the 4 to 20 milliamp signal value. HART loops. Most commonly, a 250 ohm resistor is used to convert the loop current back to a voltage. At 4 milliamps, a 250 ohm resistor drops 1 volt. At 12 milliamps, a 250 ohm resistor drops 3 volts. And at 20 milliamps, a 250 ohm resistor drops 5 volts. The load resistor can be internal to the controller or external. It serves as an aid to get the signal back for the HART communicator. A positive advantage of the 4 to 20 milliamp analog sensors and transmitters is that the signal can be carried great distances without any significant signal loss. 1000 meters. 4 milliamps is a live zero, and a broken wire would result in 0 milliamps, and the DCS or PLC system will flag a broken line if 0 milliamps is sensed. Analog sensors can send only one value to the control system. An analog to digital converter A to D with 16-bit precision can report the range of values for an analog sensor in 65,535 increments. So, for a 0 to 1000 psi transmitter, each bit represents a change of 0.015 psi. This is the 475 communicator, and we're going to show you FOSCI mapping guide, which is that big white diagram. Note the FOSCI sequences are only applicable to the 475 communicator. FOSCI does not apply to the Trex communicator. AMS Trex device communicator. That's what it looks like. That's from the bottom. Depending on the attached communication module, the Trex unit lets you configure HART and Foundation Fieldbus devices. Power one HART or Foundation Fieldbus device. Measure current and voltage. Perform diagnostics on a 4 to 20 milliamp current loop or Foundation Fieldbus segment. The Trex unit includes a color LCD touchscreen, a lithium-ion power module battery pack, and a processor, memory components, and optional communication modules. Chapter 5. Why modern plants use digital protocols. The advantages include less wiring, remote calibration, remote diagnostics, automatic configuration, reduced downtime, predictive maintenance, better accuracy, asset management, lower maintenance costs. Chapter 6. Simple communication example. Pressure transmitter sends a signal and measures 75 bar, then converts the measurement into digital data, then sends the data through communication cable, then the PLC or DCS receives the information, then the operator can see the following: pressure, sensor health, calibration, the device tag, alarms, and serial number. Summary. Industrial communication protocols allow intelligent field devices to communicate with computers, PLCs, and DCS systems. Without communication protocols, modern process plants would not be possible. Protocols allow configuration, calibration, diagnostics, fault finding, asset management. The three most common protocols covered in this course are HART, Foundation Fieldbus, and PROFIBUS.